Today we are here in a journey, okay? So let's start a little bit about the journey of data that we had in the group. And let's talk a little bit about the math behind the CityScope. So as we were explaining, the CityScope is a tool that is working with data. And at the end of the day, we try to measure something. In this case, we are trying to measure the socioeconomic and environmental impacts of the city. But the CityScope was not like that at the beginning. 10 years ago, when I arrived to the group, Ken had the CityScope as a visualization of data. It was like a visualization tool of the different models of the city. So it was about the current state of the city and how can you visualize that data. So one day, Ken was like, hey, Luis, what if we start measuring KPIs? What if we start measuring the socio-economical and environmental indicators of all these models that we have? And I was like, wow, that's, that's a challenge. And then he was like, oh, Members Week, by the way, is in a couple of weeks, so let's, let's have something running. So, of course, in that panic moment, we were like, okay, so Ken, how can we start? And with the team, we were starting to look into different ways of measuring these KPIs. And it was Jane Jacobs, of course, that an urban planner, that she was quite famous. And she was, in her book, was talking about density, proximity, and diversity as the key indicators to measure the city. So we were looking into that. And since it was kind of difficult to have like a generic tool to measure everything, we need a use case, and that's how we start focus on WOLP. But as you can see, this was the first radar where we were already looking into density, diversity, and proximity. We had energy all the time under the radar. We include energy because we thought it was quite important. And we started putting all the mathematics together, and we started looking into the case study of Kendall Square. So then we made the first iteration with Kendall, and this is a little bit the radar of Kendall. We will go through that. So in parallel of all the socioeconomical and environmental indicators, it was like, how can we match density, proximity, and diversity with the socioeconomical and environmental indicators? At that time, it was not that clear, so we put these two other kind of energy bars over there, and we realized that the Kendall was not doing great in terms of environmental impacts, and the social performance also was kind of low. So we started looking into that. So how did we get into this kind of diagram or radar? It was again going through density, proximity, and diversity. And what is density? Density is very easy to calculate. I think everybody knows how to calculate density. It's the number of people divided by the area. We have different densities in the city, and the whole point of just density is not telling us that much, because you can have very dense cities that they work very well, and very sparse cities that they also work very well. So we start looking into different types of densities. Okay, so we were like, okay, what is the residential density, employment density, third places density, so all the amenities, so and the cultural density. So we were at that time already starting to look into that integration between the socioeconomical and environmental indicators with density, proximity, and diversity. But the problem here is that even if you know how to calculate these guys, they are totally different domains, okay? So you are mixing apples with oranges and whatever. So you need to make this kind of normalization where you try to put everything on the same, let's say, yeah, normalizing is putting everything in the same kind of scale. And that was something also that requires some work and some research. How can we do that? And the second thing was like, how important is each of these indicators? So also we were looking into different papers and talking with the community, and some communities, they were giving more relevance to, let's say, employment density, because maybe they had a crisis of employment, or other communities, they were talking about cultural density. Yeah, how many, venues of cultural assets can you have in the community? So it was very important, like the communities that we were working with, being able to work with the radar and decide a little bit what was the most relevant element for them. So that's why we include in the radar this kind of weighting element. So then, in terms of density, if we look into Kendall, I think everybody, and you have also to imagine Kendall 10 years ago, that was more, even less housing, less amenities, less. So what we saw is that employment was kind of high in terms of density, but residential was super low. No? So that's things that we were looking at in the radar. And also like third places where like at night, Kendall was I think it's still kind of empty, but at that time it was even worse. And of course, as I was explaining, the generation of CO2 was very high, and the social performance was not great in terms of well-being, security, innovation was good, but in the total balance was not great. So what we were doing is, it was like, okay, what if we increase the global density? And we were starting to have this kind of outputs, okay, where increasing different densities of different elements, like housing, for instance, it was already impacting into the social indicators. So that was kind of the first iterations that we have. In terms of diversity, the same thing. So when we talk about diversity, it's kind of important. Why? Because nature is based on diversity, okay? I am putting always this video because when I talk with people that are in the financial world and people dealing with economics, they are saying, listen, the economics is big fish, it's a small fish, and that's how the world works, because nature is like that, isn't it? It's like, Luis, don't think about that, this is nature. And well, I was like, well, that's kind of weird. Then I made my research and I realized that 90% of the natural ecosystems are based on mutualism. It says collaboration, but it's more mutualism. And this means this bird, the colibri, has changed the beak to eat, and the flower has changed the shape of the flower to pollinize during millions of years. In this mutualistic kind of ecosystem, both are selfish, but they are positive selfish. So they are not trying to destroy each other, they are kind of in a collaboration, and that is what makes an ecosystem very resilient. So diverse ecosystems, they are super resilient. Why? Because when one species disappears, other species take over that gap, and they can adapt. You have just monoculture or mono species kind of ecosystems, nobody can adapt. So something that destroys one species destroys the entire ecosystem. So that's kind of very basic. So predation, predation is what we are basing our society and our economy on, and predation is only 4% of the ecosystem, and is used to clean the ecosystem from, like from sick animals, from weak animals. And the problem of predation is that as you clean the ecosystem of these kind of animals, then you start making the predation on your own species. So that's kind of dangerous, and I think that's a little bit the moment where we are right now, where we are starting to eat each other, which is, I don't like it, but but this is important. So why diversity is important in ecosystems is because of that, and in human ecosystems, diversity brings innovation. This is a little bit what I was explaining about mono species, how they always have kind of gaps. But when you have a diverse ecosystem, you never have a gap in the, it doesn't matter what is the output of the ecosystem around it. The problem is that if we keep, as humans, this kind of predatorial approach, what we are going to have is this, what I call the IoT bubble tower, because you are going to have systems that they don't talk with each other, and then what is happening is like competition, and even if you have huge and beautiful technologies and systems, if they don't collaborate with each other, what you have is silence. No? It's like a little bit the Babel Tower in the Bible, where the different people started speaking different languages, and then they could not communicate. Is exactly what we are today. No? Systems are not communicating. So the funny thing is that one day we were trying to understand diversity in cities, and we had no idea how to measure that. So we learned all about these kind of natural ecosystems. Having coffee here with we were having coffee with a person, and she was like, listen, she was from the world of natural research, so she was like, have you looked into Shannon index? And we were like, Shannon index? I have no idea. So this is a mathematical approach that is coming from natural ecosystems that when you use it in the city, it works, which is very interesting. So cities, when I say a city's ecosystem for the humans, is kind of true, because a lot of the mathematical equations that work in the natural ecosystem works in a city, at least between human interaction. Once again, we have different diversities that we kind of calculate, and we did the entire process of apples to apples. So in Kendall, the diversity of employment was kind of high. Now, actually, this has a shrink because most of the industry now is becoming biotech. So that's kind of changing now. But the residential diversity was very low at that time. And again, when we were starting to play with these numbers, we could see how the social and the CO2 generation was changing. And then proximity. Proximity, there are many, many ways of making a calculation of proximity. Actually, every time that a student gets into the group, is kind of measuring proximity in different ways. So it's fantastic. The simpler one is this one, where you just get the center of a cluster, and then you find the shorter path. But when you do this in cities, you have to do like Google, and you have to look into the roads and how that is not the shorter path. You have to always follow a road. So, but proximity, what it was giving us, it was connecting with other elements like proximity to park, public transportation. It was giving us a lot of the social element, because if you don't have proximity to, like the assets that, gets the humans together, like the parks and the transportation, etc., it's very difficult to have a well-balanced ecosystem. And again, well, the amenities in Kendall were very bad. And the cool thing is that when we were bringing, more access to the amenities, the radar was even getting better and better. So this is connecting with the walkable city a little bit, this idea of everybody having walkable access to different amenities. And okay, so that was kind of the beginning. But then we were like, okay, this is, so that was 2013, 14. Then we start having access to real data, telecom data, through the Andorra project. So we were able to have big amount of data to start validating the KPIs. And we were in communication with Marta Gonzalez and other people at MIT. Now she's not at MIT, but she's a great professor that she was with other groups as well, validating all the, let's say, ideas from Jane Jacob through telecom data. So she was like, density, proximity, and diversity in the city. How can we validate that looking into real movement of people and real data? So we were literally using that knowledge and using that knowledge for our research, which is pretty cool. So because before we only had like a, let's say, aggregated indicator of, let's say, access to parks, etc. Now we could see how access to parks is really, really, giving, for instance, better quality of life, because we could literally correlate telecom data with behavior. A good example here is in Andorra. No, I think I have showed this many times. In orange, you see the Spanish people. In blue, you have the French people. In white, other nationalities. And here we are looking into the behavior of people. But this heat maps is already a numerical number. It's giving us the level of congestion on that place. So you can see also the level of pollution on that place. You can see many things. You can translate it in a more visual map that everybody understands. So red is congested roads, green are roads that work. So we start saying, okay, when you make, you have the radar to make the aggregated KPIs, but then you can have a fine-grained kind of understanding of that information in a map. And that was fantastic. And then Kent was like, okay, this is fantastic, so we are good, but we need to find some kind of prediction tools. So how can we predict things through these tools? And that's how we jump into the zero carbon cities model, where Kent was like, okay, there are models out there, like En-ROADS, that is fantastic, to be honest, but it's more a global model. It's difficult to be more focused on communities. It's more like the global planet. And it's measuring mostly like just the CO2 emissions, but what about the socio and the economical impacts, etc. So we were kind of, so Kent was like pushing us in, can we have like a community model? So then what he was saying is like, he called me, I always make this joke because it was, again, before Members Week, and Ken was like, we need to have a model, blah, 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 blah. Please, what do you think if we put everything together and we have a model in a couple of weeks? so I was like, so I think this is the joke. I just removed Kent, but so I was like, I think the best thing that we can have is a ballparkish kind of model. And that's a little bit what we had as a first iteration. I always say, no, we do research through iterations and we learn through the process. So this was like the first approach to that, like, yeah, we can have a ballpark-ish kind of figures. That means that we translate everything to CO2 equivalents. That means, like, you have when we talk about CO2, not just CO2, okay? So we are taking everything related to, like there are, I think, I don't know, a lot of different gases that they made the green gas, the environmental impacts. So we take all the gases that they are not good for the ambient, and we put it and we translated that into CO2 equivalent. Same thing with the kilowatts hour. Also, we were working with average numbers. We have linear correlations, a lot of them, a lot of extrapolations, and some educated guess. No? So that was kind of like the first model that we did. This is a little bit the explanation of how we can translate kilowatts hour to tons of CO2. So we were using also models from other people. Of course, we always try to have the life cycle assessment. I don't know, I mean, we have been talking about this, but is clear for you like how this works, like the life? When you look into materials or buildings or cars or whatever, you always have to keep in mind the life cycle of the materials. So from the moment that you extract the material, you put it into the factory, you build the car, you put the car on the road, you use it, then you recycle or trash. Then in all that process, you are consuming energy, okay? You are having environmental impacts. And when you get the material and you produce the car, that's embodied CO2, because this energy is producing CO2, so that car has already embodied all the energy from the extraction to building the car. Here, when you are using the car, that's operational CO2, okay? Because here what you are doing is you are consuming all the fuels or whatever you need to move the car. And then when you trash or recycle the car, then you also have embodied CO2, because so that means that a lot of times when we measure the CO2 in the planet, and we say, for instance, China is producing a lot of CO2, that's not super fair most of the time, because a lot of that production is being used in a different country. Maybe they are producing the car, but the car is used in UK, whatever. So that CO2 shouldn't be just attached to China, it should be attached to the people using the car. That's something important, so we were using this for the model, which, and then also, I don't know if you're familiar with how do you measure the CO2. So this line over here is the embodied CO2, okay? This pink line. So you have all the CO2 that you have need to produce the car, and then you divide it in 10, 20 years, depending on the life of the car. Okay, so that's why it's homogeneous, but this is the car. And then when you are using the car, you start having like the operational CO2, okay? And this is kind of increasing because you are using that operational. I think that's I like this diagram because I think it's kind of clear of operational CO2 and embodied CO2. With that, I built this first iteration of the model that is kind of complex. Today, we have to decide if we are going to use this or another model. But at the end of the day, here in this model, what we have is the traditional radar that I was explaining before, but also you have the kilowatts hour that you can consume and the CO2 emissions, because with some policies you could reduce the CO2 emissions, but you could keep the kilowatts hour. Okay, so you could. There are some solutions where maybe you keep producing energy without the production of CO2, and then here you have the policies that you can use, like I don't know, life work symmetry. That's a walkable city, percentage of electric vehicles, hybrid work, building retrofitting, walkable amenities, etc. And here you have kind of like the energy source that you can use for the producing the energy. So that was kind of like the first model that we did. But then we started refining the model, and Kent was like, "Yeah, I like the ballparkish, but I want to have at least a ballpark. So let's remove the ish, and let's have something more. It's not perfect, but it's a next iteration." And that's what I call the tool, and I can explain this in the first class a little bit. I'm going to go a little bit more in depth, but the whole point is how can we get by 2030, 2040 into balance or net zero Kendall square. So for that, what we did was like taking all the data of everybody that they were working and living in Kendall Square, there are approximately more than 20,000 people. So we were understanding the behavior through telecom data. We were measuring the carbon footprint of all of them. So as I was explaining, if you are using a house during 5 years, the CO2 embodied in that house is going to be attached to your carbon footprint. If you are using this car for 1 year, that CO2 is embodied to you. If you are using a plane for 3 hours, that CO2 is embodied to you. So it was kind of like that's how you build a little bit the carbon footprint, again, through the entire life cycle of the different things that you were using, okay? So that's kind of, it was kind of a complex process. Of course, we use the CityScope, and you know that, as we were explaining, the average carbon footprint for everybody, for each person living in Kendall Square is 17.19 tons of CO2 per person. It's not that bad. It is bad, actually, but it could be worse because the average in the US is over 20. It's around 22, 25. In Europe, is above 10. Other countries, they are already under 2.5. That's the goal. And Ken explains, actually, 10% of the planet, we are the problem of the 90% of the rest of the planet. Because it's 10% of us that we are over the 2.5%. So that's something that is kind of good to have, good to know. And then what we were doing in this model was like, we have some interventions. So what if we look into the interventions? And this is important because today you are going to be playing with interventions. So let's look a little bit on that. So the decarbonization of the grid by 2040. So this is important. So when we talk about the decarbonization of the grid, actually, you could imagine that if we decarbonize the entire grid and we have clean energy, all the operational CO2 is gone. That's not exactly the truth, okay? So you will remove a lot of the operational CO2, but even in order to produce that energy, you always are going to have some CO2 impacts. So, okay, so that's the first thing, and that was a first bummer for me because I was like, no, clean energy, blah, blah, and then Andres, that he was working on the energy part, he was like, Luis, no, we still have some environmental impacts. The other thing is that there is a lot of stuff that today we are doing outside of the grid, like, for instance, cars. No? The cars, they are not using the grid yet. But if we electrify, and looks like we are trying to electrify everything is going to be plugged to the grid. So some of the measures, when we say, no, then what if all the cars became electric? That's going to have an impact in the grid. Okay, so you have to see the correlation between the different policies because some of the policies, they're impacting in the other elements. So that's something important because that's why it's not super straightforward. But let's start with the decarbonization of the grid because when we talk about the decarbonization of the grid, we have to follow the government because they are the ones that they are deciding, they have the plan to decarbonization. And we are looking into 2040. So Massachusetts, by 2040, is going to decarbonize only 40% of the grid. So that's the only part that, no? So from 100 emissions, they're going to decarbonize just 40% of that. That means that it's great. I mean, like, it could be worse. There are places that they are not decarbonizing at all. But it's 40%, so that's why when we look into the bubble, we are going to reduce just 1 ton of CO2 per person, more or less. Let me throw that. So that is not bad. I mean, like, again, you went through this, so it's a little bit more than 1 ton of CO2 per person if we decarbonize 40% of the grid. So what we have had in this presentation is the bubble that is going to be focused only on the CO2, and this other radar that is going to show the socio-economical and environmental performance, okay? So when you decarbonize the grid, at the end of the day, you are not bringing so many jobs to the community, and this is the impact in the community, okay? You have some, of course you have some environmental impacts, that's why the radar has not grown a lot, only a little bit. And you have some social impacts, but it's not huge. What if we electrified 100% the cars? No? This is what I was explaining before. Then all this, let's say, oil that you are burning now in the car, it's not going to be burning the car, but you need to produce the energy somewhere to give it to the car. So these guys, they are going to shift from taking the energy from the gas station. They are going to start getting that from the grid directly. They are going to plug to the grid. So that's why now, when we are making 100% electric cars, our operational energy in the grid is growing. Okay, that which is kind of in the model is complex. That balance is happening there. When you are reducing some impacts as well, the problem is that even if you every single car becomes electric, okay, they are becoming more efficient in terms of operational CO2. The embodied CO2 is higher. Okay, so I have this graph here that explains a little bit. So this line, the red one, is the gasoline car. Okay, and the other lines, they are different electric vehicles. Okay, this is the embodied energy in the electric car, in the combustion car. This is the embodied energy in the electric car. Okay, so as you can see, because we have a battery, because we have the embodied energy in the electric car is kind of bigger. So actually, if we imagine that you get a car and you trash the car in the second year, it's better if you have a gas than an electric car. In some of the electric cars, also some of them, well, at least these ones, they are worse than the gas car because they are starting already with embodied energy, okay, very high. Of course, the new generations, they are much, much better. So it depends a little bit on when do you get rid of the car, and if you exhaust, let's say, the operational life of the car, and how efficient is the electric car that you are changing. So that's kind of important. So that's why when you bring electric cars, the reduction of CO2 is also like, 0.75 tons of CO2. So that's okay, but as you can see, the mathematics behind is kind of complex. So now also we look into the socioeconomical impacts, getting better. It's not bad. Okay, we are having some good socioeconomical impacts. Hybrid work. What if we start working at home? So it's funny because when I started making these presentations, a lot of people thought it was during the pandemic. They were saying, okay, cities are going to be empty forever, and this is what is going to happen. No? This is Madrid. This is my city and empty. I love this movie because it shows, okay, I think it is very clear for us now. I have been updating this graphic, but so at the end, what I am just putting is changing the number here and just making the line. So as you can see, before the pandemic, we were not working at home, but in 2019, 22% of the people were working at home. Then during the pandemic, 41%. And since then, we are almost back to normal. Of course, we are in 27 in the step of 22, but so I think this is kind of like what is going to happen. So we are taking that number, like what if 27% of work is happening from home? Then we can reduce even less than 0.5 tons of CO2 per person. And the socioeconomic impact, not really big, okay? Building retrofitting, what if we retrofit all the buildings? And I think I'm missing some slides here, but that's okay. So the whole point here is when you retrofit the building, is first you are bringing better isolation, that's for sure. You are making the smart buildings probably, so they are more efficient on how do they handle electricity, air conditioning, etc. But again, that's a lot of embodied energy, so you have to produce isolation materials that they are actually in terms of environment, they are not great. Also, what you have is like to remove old systems and put new systems in the building. So you are removing material and putting more material. So when you retrofit a building, the embodied energy of the building is growing like crazy. Of course, you are extending the life, so you can extend a little bit the life of the building. And also, you are making more efficient in terms of operational energy, so it's consuming less operational energy. But the final balance, even if it's good, is also only 1 ton of CO2 per person. So again, it's not bad, but it is like not the biggest impact. And then we are growing into some economic and and environmental impacts, which is good, yeah, because you are building some jobs in the community, so they can retrofit the building. So what we are doing is we are making air conditioning more efficient, so the operational CO2 is lower, but the embodied CO2 is higher. Also, you are removing some systems to make it more efficient, and the light, etc. Same thing, smart, but also the thermal isolation again. So that's, you are reducing a lot the operational, but you are bringing more embodied CO2 because you are bringing materials to the building. Anyway, so we have run out of the silver bullets, the traditional, measures that we have. So what is next? How can we keep reducing that CO2? No? Everybody's talking about electric cars, building retrofitting, working from home, decarbonization of the grid. So what is left? We still have a lot of CO2. So what we started doing was like, what if we look into the traditional approach that the group has for improving the socio and economical KPIs that we were learning a long time ago in the radar through Jane Jacob. What if we implement these kind of things in the city? So what if we start with this idea of life-work harmony, this idea of people living and working in a walkable distance? That's how cities they used to be during more than 12,000 years. No? You used to have a diverse group of people living in a dense city, and that's what it was bringing innovation. So what if we look into that? Actually, not that long ago, my parents, when they moved to Madrid, they were like, I want to have quality of life. So they were always looking at a house, close to the school, close to the park, close to the amenities. So what if we have that, 20 years ago, okay, I am older than 20 years ago. Let's say some years ago, my parents thought that was quality of life. So we have modeled that approach because more than 40,000 people commutes per day to the Kendall Square area. So 40% of people, 40,000 people, that's half of the Andorra country. The country of Andorra, there are 80,000 people. So it's kind of a lot of people commuting to Kendall every day. So what if we have everybody living and working in a walkable distance, from the CEO to the people cleaning and cooking, living in that walkable distance? So for sure, what we are doing is not only removing time of commuting and operational CO2 from the cars, but also what we have is like inefficient one-family houses on the outside of the city. What if they start living in these efficient buildings that we have in the city? Because again, these policies, we have put it one after the other. So now the buildings in Kendall Square, they are very efficient in terms of energy performance. So what we are doing is changing a very inefficient house with a more efficient building. And also we are reducing commutes. So we have some numbers for that, because for the social and economical part, what we are also trying to figure out what is the mathematics of understanding this kind of self-content or and it's not our mathematics, this is also coming from different articles. So we are always, if somebody is doing something good, we don't have to repeat it. We just borrow the math and we try to use it in our purpose. So that's how we measure the socio-economical impacts. And of course, if we do that, Kendall needs to increase the density of housing. So that's part of the, we have made a couple of iterations. So we have made different tools. Also, we were looking into how can we incentivize people to move into Kendall Square. So this is a model that Ryan did about incentivizing different prices in the housing to see if you could really incentivize people to live in Kendall Square. Anyway, after some research, what we have realized is that you can reduce almost 3 tons of CO2 per person just by going back to quality of life. But since, and this is something that we already knew, is like when you have these vibrant communities, people living close to each other also are having a very good socio-economical impacts as well. So that's kind of something is kind of like a win-win-win. No? Like technology will not only solve the problem of climate change, but also like having resilient communities can help a lot. Of course, in parallel, what we need is to have walkable amenities. Because now, and mostly in the United States, in places like Texas, 95% of the movement of the people is by car. So that means that even if they are going outside to get milk, they will use the car. Go outside, I don't know, I cannot imagine. I mean, if you have a dog, maybe you are with the car and the dog, I don't know, because 95% of the movements in Texas is by car. That's crazy. So in a culture like in the US, the walkable amenities is quite important. There are other places where, and this is quite important, the model is focusing Kendall. In other places, as I was explaining, we have different carbon footprint, but in the US it's quite big how the walkable amenities are impacting, because it's not only about the amenities that we are missing in Kendall Square. So we were using replica and SafeGraph data to understand how people are moving in the city, shopping, and doing other activities. And also we were looking into the amenities that we need to foster a community. So now that you have a diverse community in Kendall Square, because we have bring everybody, that 40,000 commuters, now they are living in our model in the city, okay? But then the students probably they're gonna have different needs in terms of amenities than, I don't know, the CEO of the company. So probably some people are gonna prefer to go to the Burger King, other people will prefer to go to whatever, no? So you have to bring also diversity of amenities to the neighborhood. In any case, we were looking into what amenities we are lacking in Kendall Square, and this is all the amenities that we are lacking in order to just support that community. So that's a lot. And when we are looking into lack of amenities also and distance, we were building models where you don't only have the horizontal access, also you can see vertical communities, like how far are they from different assets. So in red, you see the lack of access to different shops and amenities here through these models. The most important thing is that here it's not only about people walking to the amenities, it's like also instead of people going to a mall, these huge spaces for shopping are very energy inefficient. Because they are huge, they are conditioned the entire thing. So in this model, what we are doing is like, you don't need the mall because you have this kind of a small or more like community scale kind of shopping that is much efficient in terms of size and energy performance. So that's also why we are reducing like 2.5 tons of CO2. So when we talk about walkable amenities and walkable cities, it's not about just walking and having sidewalks and having bike lanes. No, it is about land uses and how that land uses, moving that land uses can change not only the movement of people, but also the environmental impacts, of course, the social impacts. And as you can see, like when we look into the socio and economical impacts, they grow. And now we have a bunch of our technologies that even if they are going to have a smaller impact, they are needed in order to bring diverse people into Kendall, because, for instance, robotic architecture, what it can help is to have more affordable housing. Now we have a crisis of housing, so what if we have these small houses that they are more affordable for people? You already went through this with Asier, he was explaining already. So if we deploy robotic architecture, we can have a small environmental impact, but we can keep growing on the socio and economical impact, because this is helping young entrepreneurs to live in Kendall Square. Autonomous vehicles, again, Naroa was already explaining this. I am not going to explain more, but something that is important is just by the impact of the reduction of the fleet, we are reducing a lot of embodied CO2 of the bikes that we need in the system. So that reduces around another half of ton of CO2 and increment the environmental impacts, the socio-economical impacts. The food, I think we have not talked about this, but food is, this is very related to local production, okay? So food in the United States, the average impact is 2.5 tons of CO2 per person. So our habits on food are not great in terms of environment. So, but it's a combination of how do we make the food and how far it's coming from, and also like yeah, like how do we make the food? So what if we shift a little bit in a more, let's say, you know, like a vegan or in diet, but what if we also try to produce it locally? No? So the whole point is a combination of different factors. Eat less meat. That meat has a huge impact in terms of environment, mostly because how we grow our cows. But what if we still start having in the city some kind of local production, maybe in the parking lots that now in our model we don't need that many parking lots because we have removed the cars. We have this micro-mobility now going on. So what if we start having local production of food over there? That can help to reduce 1 ton of CO2 per person, which is a lot. Some other social impacts, and just because we are finishing, we were looking into the decarbonization of the grid from the government, and they could only decarbonize 40%, okay? So now we are at the end of the chain. We have tried all the different policies. So what we are saying here is like, what if as a final policy, we just decarbonize the rest of the grid? So what if we use very dense, high density power, like a spark, and we help to decarbonize the last piece of the grid that has not been decarbonized until now. So then we can, again, reduce another ton of CO2. Now we are going to have a beautiful radar plot all round. Okay, this is a little bit, you know, like just for the fireworks, but I like to show that. And then, as Ken was showing in his presentation, this is how far can we go with in cities, because cities, they produce 70% of the CO2 emissions. And as Ken was explaining, is like, yeah, other things that we have to do, of course, is the decarbonization of internet. Internet produced 7% of the CO2 of the planet. The last time that they measured, that it was 2022, 7%, if you look into the world, India produced 7% of the CO2 of the planet as well. So our data produce as much energy, CO2 than an entire country of millions of people like India. So that's quite important, but also trying to foster more clean air traveling. And of course, trying to have as much as possible local production can help us to get into that 2.5. This is the win-win-win that Ken was always explaining. So the green part is the second radar that I was explaining, how it is impacting into the different parts. And again, so this is how we have been build the model, and this is how we were like playing with the different policies, but it's not the only way. And these are not the only policies. So this was like our kind of approach, but the cool thing is that probably people can have new ideas, people can have new technologies that we could test and prove, and also you can move the policies around, and you can see what is more important. Maybe we don't have enough money for one policy. And I think the exercise that we are going to have today is a little bit about that. Because, why? Because, I mean, I think the kids are asking us for a solution, and we cannot be like saying no. I mean, like, so this was right before the pandemic, and I think we forgot about them. It was the kids, they were like, we need to have a new solution for the planet. Now we have the pandemic, now we have, the world has some troubles with wars, and we forgot a little bit about climate change. Actually, there is a huge pushback in this direction in Europe, in the United States. And so I think it's our role a little bit to keep focus, laser focus, because I am not worried about AI conquering the planet. That's not going to happen in the next 100 years. I am not worried about many things. I am worried about this. I mean, this is happening now. So we should figure out how can we work together on that. And this is the end of the presentation, but I want to finish as well with, if you are interested, now we have the bubble at the MIT Museum. That's, by the way, that's Maitane's Nora. That's Maitane's daughter playing with the bubble. And so if you want to play a little bit with a very simplified version of the bubble, you can go over there and see it. And let's see, we are going to try to, I mean, we are building, this is under construction, okay? So for the class, we were expecting to have it already ready for you guys. So we have built this tool where you can play with the policies. and then you can see the CO2 reduction per policy, and then you can also play with the policy. So you don't have to follow our path, you can make your own path. The only challenge is that it's under construction. So we are not sure if the numbers are perfect, if it's gonna work perfectly. I think we are gonna give it a try, so you can play. If it doesn't work, then we could use Excel that I did this ballparkish Excel, but I think this is better because the exercise with this, the idea is that we are gonna give you, as Ken was explaining, we are gonna give you a budget, and then with that budget, you have to figure out how much CO2 you can reduce with that, okay?